Hello everyone, we are group number 15. Today we are here to discuss on the topic comparison of object fixed projections and center of projection fixed projections. So, have you ever wondered how different perspective can change the way we see the world around us? Yeah, the way we project objects can change our perception. So, today we will explore two different types of projections. They are object fixed projections and center of projection fixed projection. And understanding these both projections can help us to uh, compare them both and used in applications. So basically, projections play a vital role in how we interpret visual data. In this presentation, we will be discussing these projections and give a comparative analysis followed by an example at the end. So, uh, basically, what is object fixed projection? Object fixed projection maintain the orientation of object relative to the viewer, whereas center of projection fixed projections is characterized by a single fixed viewpoint from which all projection lines radiate. So briefing about object fixed projections. In these projections, they focus on representing 3D objects on a 2D plane, maintaining the object's fixed position relative to the viewer. In this projection, the shape, size of the object is not changed. I mean, the object is not distorted. So there are basically several common types of object fixed projections. Those include orthographic projection, isometric projection, axonometric projection, and oblique projection. Briefing all these projections, orthographic projection, in short, is it shows an object in true size using parallel lines without perspective distortion. Whereas in isometric projection, it displays an object with equal scales along an angle of 120 degrees. And axonometric projection, it represents the object in different angles to show multiple sides. And lastly, in oblique projection, it shows the object's front face in true scale, while the depth is represented at an angle. So, and a few of the characteristics of this object fixed projections include lines drawn from points on the object to the projection plane are parallel to each other. And as I've said earlier, true dimensions and shapes are maintained, and there is no perspective distortion. It is also useful in technical engineering and architectural drawings. Few of its applications include engineering and architectural drawings, and also in CAD software where 3D objects are represented on 2D plane, and also in technical illustrations. Few of its advantages include accurate representation of dimensions and easier to measure and interpret technical details. And lastly, coming to its few of its disadvantages, there is a lack of depth perception and can appear unrealistic compared to COP projection.
Okay, now on the other end of the coin is center of projection fixed projections. Unlike object fixed projections, the center of projection fixed projections stimulate how a human eye or a camera works. Okay, so in this, the projection is taken on a fixed viewpoint, which is also called as a center of projection, which results in perspective distortion. That is where the parallel lines, the lines which seem parallel to each of the vertex of the object, seem to converge towards points called vanishing points. So in next slide, uh, in the as you can see in the image, the lines with parallel lines passing through the vertices converge to a point called the center of projection. So it gives the illusion of the size, the relative size of the object being changed as the distance changes from the center of projection. And as you move the objects farther and farther, they appear smaller and smaller. This mimics human vision and adds a sense of depth to your perception for the camera or the eye. And it also creates a more realistic and more visually appealing representation in application like games and in modeling. Next slide. Okay, there are broadly there are three types of projects. The center of projection fixed projections. One is the one point perspective. In this, all lines parallel to one axis converge to a single vanishing point. That is, an axis passing through a vanishing point or a center of projection. With respect to that, we get a perspective projection. And there is also the 2 point perspective, in which two vanishing points are taken into consideration, and lines parallel to these two axes converge to two separate vanishing points. And in the 3 point perspective, it's the same thing, but here we take into account three vanishing points, and three axes converge to three different vanishing points. And 3 point perspective is also called as a bird's eye view of an object. Next slide. Okay, so characteristics, as I discussed, parallel lines in center of projection fixed projections converge to vanishing points. That is the points from where the seemingly parallel lines seem to originate. And the objects appear smaller as they move further and bigger as they move closer. And as discussed earlier itself, it mimics human vision and adds a depth perception of depth. The application of these are, as I discussed, video game. They look really good as representations in video games and animations, and this particular thing is very crucial in virtual reality, because in virtual reality the main feature is to mimic human vision. So, and it is also used in artistic and architectural rendering of objects as well. And coming to the advantages, as I said, it realistically represents a scene along with its depth perception. And because of that, it appears like any of modeling is true to life, like it appears true to life because of the added sense of depth. But the disadvantages, as I said, the object gets distorted from its true dimension. That is, you cannot actually gauge the absolute size of the object, as it is distorted due to the increasing distance between them. So the measurements are not straightforward as well. So that is about. And next slide. So what are actually the differences? To sum up, the differences between object fixed projections and center of projection fixed projections, we have a few criteria on which they differ. Firstly is the orientation fixed relate in object fixed projection, the orientation is fixed relative to the object, and in center of projection fixed projection, the orientation is fixed related to the viewpoint, that is the vanishing points that we have discussed. And dimension accuracy, as I discussed, in object fixed projections, the measurement is simpler due to the true dimensions being preserved, while the true dimensions are distorted due to the parallel lines converging to a single point. And parallel lines remain parallel and they converge to vanishing points in center of projection fixed projection. And depth perception is present in object fixed projection and absent in center of projection fixed projection. And the complexity in measurement, as I've said earlier, it's difficult to measure, easier to measure in object fixed, and easier to complex to measure due to distortion in center of projection fixed. Okay, and visual appeal, object fixed projection, they are more technical and have absolute measurements, but they appear more bland and more artificial in comparison to center of projection fixed projection. And use cases are CAD drawings and technical drawings, where you need to have your dimensions absolute in every frame. While for artistic renderings, video games, center of projection fixed projection is preferred. And advantages and disadvantages we have discussed earlier, so we can skip that. Next slide. So,
Now let's dive into the process of converting an object fixed projection to a center of projection fixed projection. This process requires a series of transformations to align the scene properly and project into a plane. Now let me walk you through the steps. Firstly, we identify where the side vector extending from the viewpoint to the object intersects the projection plane. For simplicity, this plane is often set at x equal to 0. This intersection point becomes the reference point for the following transformations. Translation, the intersect point to the origin. Next, we translate the intersection point so it's aligned with the origin of our coordinate system at origin. This ensures that all further transformations are applied with respect to this new origin. The translation matrix can be looked like this, that xi, yi, and zi represents the intersection points. Next slide. Next slide. Slide changing.
Yeah, slides changed. 3 and 4.
Now, once the intersection point is at origin, we rotate the side vector so that it points directly along the z-axis. This involves calculating the rotation angles and applying the appropriate rotation matrix, such as for rotation around x-axis or y-axis, the steps aligns viewpoint and the point of proper projection. Now we combine the translation and the rotation transformations into a single matrix and apply it at every point it seen properly. This step repositions both the object and the viewpoint to align with the new coordinate system. Perform the single point perspective. Finally, we project the transformed scene into a 2D plane with the perspective projection matrix. This matrix look like this, and where D represents the viewpoint and the projection plane. This projection stimulates how the human eye perceives depth, create a realistic perspective. Next.
Let's discuss an example, understanding perspective projection onto a perpendicular plane. Next slide. So our objective is to project a cube onto a perpendicular plane. So we have center of projection, which is our cube center, is 10, 10, 10, and our perpendicular plane, which is passing through a point -1, -1, -1. And we have a side vector, which is s is equal to -1, -1, -1. So our goal is to determine the intersection point of a side vector passing through the perpendicular plane. Next slide. So our first step is to calculate the equation of perpendicular plane. So first we have to find normal vector. So our normal vector is just opposite to our side vector, which is 1, 1, 1. Then our general equation of plane is ax plus by plus cz plus d is equal to 0. So after putting the value of a, b, c from a normal vector, we get the x plus y plus z plus d is equal to 0. So let's find the d. So putting the point which is -1, -1, -1 in main equation, we find the d, which is come to be 3. So after putting the value of d, we get the actual equation of plane, which is x plus y plus z plus 3 is equal to 0. Next slide. So parametric equation of side vector. So we have to find a parametric equation to get the intersection point. So our side vector is -1, -1, -1. So our parametric equation is starting point plus t times directional vector. So our starting point is center of projection, which is 10, 10, 10, plus direction vector is -11, -11, -11. So after getting the parametric equation, we get 10 minus 11t plus 10 minus 11t plus 10 minus 11t plus 3 is equal to 0, which is our parametric equation. So finding next slide. For finding the intersection. So as we get the parametric equation, we first find the value of t, which is come to be after solving the equation, we get the value of t, which is equal to 1. So we get the actual parametric equation. So finding the intersection point, we have to put the value of t in main equation. So our main intersection point is come to be -1, -1, -1. Next slide.
So we found out that this point is -1, -1, -1. So we want to translate it to the origin, that is 0, 0, 0. So we need to find a translation matrix. For that, we need to do destination point minus the original point. So 0, -1, we get tx equal to 1. Same for y and z. So the rest of the matrix is same, and this will become our translation matrix. Next slide. So, uh, so next we need to do rotation. After the translation, the normal vector becomes like this. So how much should we rotate in x and y direction such that this normal vector starts to face the positive z direction? So for the x, if we draw a 2D scenario of this scene, this is y, this is z, and the x-axis is coming out of the plane, and our vector look like this. So how much should we rotate in this axis such that this vector start facing the z direction? So if uh, this value is 1, this value is 1, and by the Pythagoras theorem, this becomes root 2. So this theta is can be calculated by cos theta base by hypotenuse, so it becomes 1 by root 2. And the sin theta also becomes 1 by root 2. So if we rotate by 45 degrees, then this normal vector starts to face the z direction in this scenario, and the vector look like this, and its length is root 2. And we get the theta to be 45 degrees. So in x, we need to rotate by 45 degrees. And the transformation matrix for such rotation is this, where this is cos 45 degree, this is cos 45 degree, the sine 45, and the minus sine 45 for the x rotation. Then we need to rotate in the y direction, y axis. So if we draw a 2D plane, this is z, this is x, and the y-axis is coming out of the plane, and our normal vector after the previous rotation looks like this, and in z direction the length is root 2, the x it's still 1. So and by Pythagoras theorem it is root 3. So how much should we rotate in y-axis such that this vector starts to face the z-axis? So the cos theta becomes the base by perpendicular, that is root 2 by root 3, or we can say it is 2 by root 6, and the sine theta becomes perpendicular by hypotenuse, that is 1 by root 3. These values are for theta 35.26 degrees. So if we rotate in y-axis by 35.26 degrees, the normal vector starts to face the positive z directions. And for such transformation matrices like this is the cos theta, cos theta, sin theta, and minus sin theta, which should be calculated here. So clearing the screen. Next slide. So after the translation and the x and y rotations, we can get a concatenated transformation matrix. If we multiply these three, we get this as a resultant. So we can use this transformation matrix on our points. So if we use it in our center of projection, which was 10, 10, 10 on the space, if we multiply it by the transformation matrix, we get the new coordinates of the center of projection, which is 0, 0, 33 by root 3. Next slide. So after doing all these transformations, our scenario look like this. The plane is passing through the origin here, and it's facing toward the positive z direction, and the center of projection went to 0, 0, 33 by root 3, and the scenario looks like this. Next slide. So as discussed before, to calculate the transformation matrix for such scenario, it's given by this matrix here, -1 comma m. Here m is the z value we calculated for the center of projection, which came to be 33 by root 3. If you put this m here, so the transformation matrix becomes like this. So we can use this transformation matrix to calculate our projection. Next slide. So after multiplying this transformation matrix to our previous transformations, we get this as a resultant matrix. This is our final transformation matrix we can use to calculate the projection onto the 2D plane. So next slide. Now we have the final transformation matrix, and this is the shape we want to okay. We want to find the projection of. So it has 1, 2, 3, 4, 5, 6, 7, 8, 9, and 2 10th in the background. And we have 10 points we want to find transformation of. So we make a simple matrix of the 10 points, and we can multiply it with our transformation matrix to calculate the points. Next slide. After multiplying previous two matrix, we get this matrix as a result. In the fourth column, you can see the values are not 1, so and they are less than 1. That means the points are scaled down. So we need to scale up those points. How can we do that? We can take this value in the row common out of this, so such that it becomes 1. We can do it for the all rows sequentially, and then the matrix convert into this. So the this matrix is our standard up to our standard scale, and these are x, y, and z points for our projection. So if we plot these points onto our 2D surface, we can get a shape like this, where this is 0, 0, which is this point, and all other 9 points can be drawn in this like this. This is our x, y plane, and this is our resulted projection. So with this, our example is completed. Next slide.
As to conclude our presentation, we have taken the basic learnings from this topic. As the fixed object has projection is very useful for technical drawings with precise scaling and fixed viewpoints. Secondly, we have center of projection, fixed projections. It we use in realistic depth and perspective mimicking human visions. We have the future scope of this topic is very useful as integration of hybrid projections for advanced 3D modeling, and application in augmented reality and virtual reality for immersive experiences. Thanks for our presentation.
Okay, this is group 16, and this is the end of our presentation for computer graphics.